All right, so welcome back. We're going to talk about gravitational force. Remember, gravitational force is one of the 4 fundamental forces. And so we're going to break this down a little more. We've already talked about the gravitational force, and we talked about how the force that an object experiences, we call that weight. So you go to the doctor, he tells you how many pounds you weigh. They're actually telling you this is how much force you're experiencing based on your location, okay, and your mass. The equation to find the weight, right? Remember, the symbol is F sub g, literally meaning force of gravity, and it's mass times g. But one thing to note about this equation is that this is only applied at the surface of the planet, okay? And so when we talk about g, this is the acceleration due to gravity, right? And we're going to kind of expand out what we've already talked about. So it's the acceleration due to gravity near the surface of a planet. So what does that mean? Once you go further out past certain points, there's something else that governs, right, our gravitational field or gravitational force. And that's what we're going to talk about, right? And that's going to be the focus of this little section. So now we're going to talk about what happens when we go, gravity acts on an infinite distance. So what happens when we get out near that infinite distance, okay? And so as you go away from the surface of the, excuse me, as you go away from the surface of the planet, okay, the gravitational force is going to get weaker, right? So it means it's going to be smaller. So you have less gravitational pull as I go out further. And one thing to note about Newton, yes, he made this discovery, but he didn't necessarily discover the concept of gravity. It was already there, but what he discovered was that it was universal. Okay, so it applied everywhere, right? And even Einstein has some theories about gravity and the bending of light around gravity and everything. Okay, so Newton's law of universal gravitation is what this is called. This is what governs the principle of what happens when you get out near those infinite areas. Okay, and so the force, and to calculate the gravitational force, we've already kind of talked about it when we did the factors of change example way back in the first video for this unit. So it's F equals G m1 m2 over d squared, okay? Where m1 is just simply the mass of object 1, m2 is the mass of object 2, okay? Now, one thing to note, this law is what we call an inverse square law. I mentioned that way back in the first video too on how electromagnetic field and gravitational field act. So this means it just varies inversely as the square of the distance between them, or between the centers of the masses. Okay, note this G right here. So this G is not 9.81, but this is what we call the universal gravitation constant. So this is a different value. I'm running out of space. So we call it big G. And it has a value of 6.671 times 10 to the negative 11th newtons times meters squared per kilogram squared. Now, when you plug this into an equation, when you write it down on your paper, you don't have to put this unit, okay? Just understanding that if I'm solving for force, in the end, my unit's going to be newtons. If I'm solving for meters, right, or distance, in the end, my unit's going to be meters, okay? And this value was discovered by Henry Cavendish using a set of rotating spheres back, I don't remember exactly when he did this. But now, R or D, okay, one thing is yes, objects go around, right, the center, but it's not the radius of a circle. The way we have to think about it, it's the distance. So it's the distance between the centers of mass. Okay, so that does change up a little bit how you do some of these problems, because if I'm looking at Earth, right, and we're going to do an example here with the International Space Station, right, and I have like this is at like 400 kilometers. Well, gravity originates from the center of the planet, so I do have to account for that. So in this case, for the equation, my r would be the radius of the planet plus the height at which this is acting, okay, or where we're in orbit, to determine the gravitational field, okay. And so here's another factors of change example. And the question is, are the astronauts on the International Space Station weightless? So you see pictures of them floating around, but are they actually weightless at that point in time? And then you justify your answer by using the factors of change process, right? And so here's our formula that we're going to look at. Oh, I forgot the G. I forgot the big G. G, M1, M2 over D squared, okay? And so our factors have changed. G is going to stay consistent. 1 is going to be, mass. We're going to do the astronaut, and we're talking about in relation to Earth. But now we got to do is figure out what is the factor for the distance, right? And so one thing to note is that the International Space Station is 255 miles above the planet, above the surface of the Earth, okay? Which is about 4.085 or 4.08 times 10 to the 5th meters. Okay, so what we're going to do is we need to figure out what is that orbital distance, like what I showed you up here. This r equals rp plus h, and so 6.300 times 10 to the 6 meters is the radius of the Earth, plus this. So this is the radius of orbit, plus this 4.08, excuse me, times 10 to the 5th meters. Okay, and so that's going to be an answer. I did not write this down on my page here. So 6,300. Just typing in some of the numbers, 4.08 exponent 5. And so this is going to be 6.708 times 10 to the 6th meters. Okay, and so what is my factor, right, between, so what is the ratio, right, of the orbital radius to the radius of Earth? Because when we compare, we're comparing what is their gravitational pull here on Earth. So we're going to do the radius, the orbital radius over the radius of the planet. So it's going to be 6.708 times 10 to the 6th. Divided by 6.3 times 10 to the 6th. Okay, and so we're going to get a factor of change of 1.0648, and that's going to go in the parentheses that I wrote down already. So 1.0648, right? And so what I'm going to do is I'm going to say, okay, what is the factor? What is essentially the percentage difference, right, of Earth versus the International Space Station? I plugged it in wrong. Put switch the 0 to 6. And so you're going to find that the factor is 0.882, which is 88.2%, right, their weight on Earth. So are they actually weightless? No, they are not weightless in relation to the Earth. Okay, well, that's one thing you need to also kind of note here. This is in relation to the Earth. If they're weightless, this would have worked out to be 0. Okay, and so now again, we're kind of building up to our circular motion. But again, this unit talks about gravitation. So we have a couple more topics to do with gravitation, and then we'll get into our circular motion or centripetal force acceleration.